last topic we'll discuss together in Chapter 11, the term phase diagrams is what I actually tried to draw before in a previous video lesson and didn't do a very clean job of it, so I can hope to show you some book drawings. Phase diagrams are three phases of matter: solid, liquid, and gas. A phase diagram, in my own mind, just simply says it's telling me things about pressure and temperature and where I would find the three phases. So a phase diagram is indeed a graph and describes the different states, those are solid, liquid, gas, and the state changes that occur at various temperature, pressure conditions. So each region represents a solid region, a liquid region, or a gas region. I'm going to show and kind of talk at the same time. This did not print well, so I'm going to go here. Let's see. On slide 115, this is a phase diagram. All right, it's what I tried to draw when I talked about carbon dioxide. All righty. This did not print well, so I'll turn my attention here. Alrighty. I have three clear different regions where temperature is on the X and pressure is on the Y. Pressure is increasing as we climb up, temperature is warming as left to right. We have in the first distinct region, at low temperatures, the solid phase of matter. The second distinct region is the liquid phase of water. And the third distinct region is the gaseous phase of water, all right, or whatever it happens to be that you're looking at. I keep saying water, but every substance has a unique phase diagram. There is a liquid gas line to represent vapor pressure. The liquid gas line separates those two phases. This is the very definition of vapor pressure. The gas is pressing down on the liquid form in a dynamic equilibrium. Both states exist simultaneously at this particular line segment. Critical point. We discussed this earlier, and that's the very point that I tried to draw. The furthest point on the vapor pressure curve. The furthest point, and typically most phase diagrams actually have a dot up here to say, past a certain point, I can no longer distinguish, and the line just disappears, and you see this blend together. I can no longer distinguish between the liquid and gas phase past the critical point. The triple point, another point of interest, where all three phases of matter exist simultaneously in equilibrium. The solid, the liquid, and the gas phase exist simultaneously at one specific point in time of pressure and a temperature. Over here, this would represent the vapor pressure. Here is the equilibrium between solid and solid and liquid. And this unusual point down here, the sublimation curve. In other words, when a solid goes directly to a gas, that term was called sublimation. If a solid melts, it's known as the fusion curve. If a liquid vaporizes, it's the vaporization curve. So the phase changes are read on a phase diagram. Phase diagram of water didn't print well, so we'll look up here. Notice on this particular phase diagram, I clearly see the critical point where no distinction between between the liquid and the gas can be found. Low pressure, very low temperature, we find the triple point for water, where all three are in equilibrium, solid, liquid, and gas. So this particular section of our chapter really is just looking at a graph and pulling out information from it. If 760 is indeed standard pressure, 100 degrees would be where I see vaporization occur. 0 degrees is where I would see a solid turn to a liquid. At 0 degrees Celsius, solid ice melts. At 100 degrees Celsius, liquid water would vaporize. So reading across the pressure finds those two values for us. At normal pressure, we can look up the temperatures of melting and vaporization. Here's a phase diagram of carbon dioxide, which is called dry ice. Clearly we can see the sublimation occurring at pretty much normal pressure. If this is room pressure, 1 atmosphere, I clearly see at approximately room temperature a process of sublimation occurring. That in other words, the solid goes directly to the gaseous phase right here at normal pressure. So that's a unique substance in the term sublimation. You will see some practice problems just reading graphs. It's a reading graph skill. Consider the phase diagram of carbon dioxide. What phase is present at each of the following conditions? Let's find 20 degrees Celsius, roughly about here, 72.9 ATMs. So 72.9 ATMs. Oh, they're plotting this for us actually. So we come up here, 20 degrees is well below 30. So here we have 20 degrees, approximately here, go up to 72.9, we're in the liquid phase. At negative 56.7, at 5.1 atmosphere, that's the very definition of the triple point, all 3 phases would be present. At 10 degrees Celsius, about here, at 1 atmosphere, about here, I'm clearly in the gaseous phase, the only phase present. Negative 78.5, normal pressure, I'm right on the line between the solid and the gas. At 50 degrees, up in this point, 80 atmospheres, well beyond the critical point, supercritical fluid. Can't distinguish between the liquid and the gas. We're beyond the critical point. Alrighty? So some problems just as easy as that one. Just reading the graph for the phases of matter. The last few topics I would call nice to know, and I won't bother going through those. I'll talk about water is extremely important, not only in nature and regulating temperatures, regulating biological functions because of its extreme hydrogen bonding. It is very unique. It expands when freezes and so forth. So nice to know unique things about water. And the last part even goes into some crystalline structures of solids, those formula units creating a unit cell. But you can take a look at those pictures. Again, just based on molecular geometry, the different shapes. We will not be building these shapes. They're just a nice to know area. And that'll conclude your Chapter 11 video lessons.